Let's talk about vector spaces and linear independence. So here is a long definition. So what do we mean by a vector space? So we say a vector space over the real numbers or possibly the complex numbers. Sometimes it can be over something else, but for us, we can think it's the real numbers or at worst the complex numbers. So it's a set, capital V, of things that we call vectors, and there are a couple of operations on vectors. Well, addition is an operation that we do between two vectors. So I take a vector plus another vector. This multiplication, I mean scalar multiplication. So I do a scalar, and by the way, the scalars, if we're talking about a vector space over the real numbers, the scalars are real numbers or complex numbers. And scalar multiplication is where I take a scalar times a vector. And it's supposed to have all these properties. Whenever I have three vectors, so I'm using this symbol, this just means that something is in a set, like capital V is a collection of all of these things that we call vectors. So this means that I have three things that are in V. And then I have two scalars, R and S, so those are in my set of real numbers, or maybe complex numbers. And whenever I have these things, I am supposed to have this long list of properties. So the sum of any two vectors is supposed to be a vector. So if I take V plus W, that's a vector. It's also supposed to not matter what order I add two vectors. So if I do V plus W, it's supposed to be the same as W plus V. Addition is supposed to be associative. So if I'm adding three vectors, it doesn't matter if I add the first two and then take the result and add the third one. That's what this means. I'll get the same answer as if I add the second two and then add the first one to that result. There is supposed to be a special vector that we call the zero vector, and it's supposed to have the property that if I add it to any other vector, I just get itself. So V plus 0 equals V, no matter what V is. I am supposed to have, for any vector V, there's supposed to be an additive inverse that we call negative V. And the property it's supposed to have is that if I take a vector plus its additive inverse, I get the zero vector. Yeah, let me just get through these. This is scalar multiplication. By the way, the things with arrows on top, those are vectors. The things without arrows on top are scalars, so R is a real number or maybe a complex number. Hopefully I remember to draw all the arrows where there's supposed to be arrows, and I don't draw arrows where there's not supposed to be arrows, but I think I'm good. So a scalar times a vector is supposed to be a vector. We're supposed to have this distributive property, so if I'm adding two scalars, which I can do because these are complex numbers or real numbers, if I do R plus S times V, that's supposed to be the same as R times V plus S times V. Here is a different distributive property because I can also add two vectors. So I can take a scalar times the sum of two vectors, and that works out to, well, what you would probably think. There is also an associative property for scalar, like the operation where I'm multiplying by a scalar times a scalar, and then the operation where I'm doing a scalar times a vector. So if I take two scalars, R and S, and I multiply them by each other, and then take that result and multiply that by the vector V, I should get the same result as if I take the scalar S times V and then take that result and multiply it by R. And finally, 1 is a scalar. It's a member of my set of real numbers. It's also a member of my set of complex numbers, so either way. And if I take that scalar and do scalar multiplication with V, I'm supposed to get back V. So All of this probably seems very obvious, but this is like we're talking in the abstract here. The obvious vector spaces that you're familiar with are like n-dimensional space, like r to the n, like R3. Your vectors are just each vector has 3 coordinates, and of course this property holds, for example, because when I'm adding 2 vectors, I'm just adding the corresponding coordinates, and so addition, like I'm just adding individual real numbers. I'm just going coordinate by coordinate. So of course, property 2 ends up being true, and property 3 ends up being true. If we're talking about R3, the 0 vector is literally just the vector that has 3 zeros in its coordinates, or in general, in Rn, n-dimensional space, the 0 vector is just the vector that has n zeros. The additive inverse is you just flip the sign of every single coordinate. That's how it works in Rn. And we know how scalar multiplication works. And all of these properties, if you have in mind, like the vector space Rn, it all seems very obvious. But the point of emphasizing this right now is that a vector space could really be anything. And I'm going to bring up at least one example of maybe not so obvious vector space that's relevant to differential equations. So, yeah, for examples of vector spaces, I mean, example A is just what I talked about. It could be n-dimensional space. Your vectors are just, you have n coordinates. Here, example B is probably a less obvious, or not what one would normally think of if they're just hearing this definition. So my vector space could be the set of all functions from reals to reals. And so what do I mean by that? Right, let's talk about some of these properties. So, I mean, first of all, what do I mean by adding 2 functions? It's sort of, you could say, the obvious definition. If I want to have a function f and a function g, what is f plus g? Well, I'll tell you a formula for f plus g. Well, probably what you would expect. If I want to, whatever I want to plug into this function f plus g, the way I figure out f plus g of this x that I want to plug in is I just do f of x plus g of x. If I want to do scalar multiplication, if I have a function f, I should also have a function cf, where c is a real number. And the way I plug something in is, well, I just do whatever f of x is, and I'll multiply it by c. So this, I mean, symbolically, this just looks like I'm moving parentheses around, but this is an actual definition. By the way, in this vector space, the vector space consisting of all functions from the reals to the reals, what is the 0 vector? The 0 vector is the function it's the function that just gives you 0 no matter what you plug in. So it's like the constant function f of x equals 0. And that's because if I take that function and I add it to any other function, I'm going to get back whatever function I added it to. Yeah. Okay. So let me maybe... Of course, I don't want to check all 10 properties for all of these examples, but let me keep discussing it for at least a little while. So let's get to examples C and D here. So C, this means that it's the set of all vectors in n-dimensional space such that A times x equals the zero vector, and A could be whatever matrix you want. So pick your favorite matrix A, and this gives you, I claim, it gives you a vector space. So like I said, I don't want to check all 10 properties for all of these, but let's maybe check a couple of properties. Well, let's check that this vector space has the zero vector. So this is like property 4. Well, we are talking about n-dimensional space. So the zero, like what the zero vector is just what the zero vector normally is. It's the vector that has n zeros. And that's going to be in my vector space V since, well, what does it mean to be in here? The important property it's supposed to have is that A times anything in here is the zero vector. And so to check that the zero vector is in here, we just have to check that A times the zero vector is the zero vector. But of course it is. If just think about what matrix multiplication means. Like I'm going across the rows of A, but I'm multiplying each one by the zero vector, so everything's going to zero out, and I'm going to get the zero vector. So property 4 checks out for C. A bunch of these properties are obvious because, once again, we are talking about members of Rn. And so, for example, property 2 holds whenever we're talking about two vectors in Rn, regardless of whether Ax equals 0. Property 2 is true for any two vectors in Rn. Same thing for property 3. Let's maybe check one more. Like, let me check. Actually, let me check, say, property 1. So for property 1, I'm taking two members of my vector space. And so I'm taking two members of this vector space. What does it mean to be members? Well, it means that they have this property. So AV is the zero vector, and AW is the zero vector. What I would like to conclude is that V plus W is a member of my vector space, right? Like I'm checking property 1 here. So how do I check that V plus W is in my vector space? Well, I check that V plus W has this property. In other words, if I replace X with V plus W, I'd better get the zero vector, but I don't just want to write that because that's what I'm checking. So we have to verify that this is the zero vector. But hey, look, matrix multiplication is distributive in this way. This is the same as AV plus AW. And what do I know about AV? It's the zero vector. What do I know about AW? It's the zero vector. Zero vector plus zero vector is the zero vector. And so sure enough, A times V plus W is the zero vector. So we check property 1. Okay, good. And so maybe, like I said before, I'm not going to check all the properties for all these examples. Let me just kind of jump around and check a few of them for each one. Let's talk about D. So first of all, what do I mean by D? This is a set of functions from the reals to reals, like example B, except I'm now also going to require that this is a function where if I take its second derivative, f double prime, plus the original function f, that I always get 0. And so addition and scalar multiplication are going to work the same way they did in example B. So it's just like we discussed about here. Let's check, for example, let's check property 4. Hoping that the quote-unquote 0 vector, which as we discussed, the 0 vector when we're talking about functions from reals to reals, the 0 vector is just the function that always returns 0. So let's check that that function is a member of this vector space. So if f is the 0 vector, meaning f is just 0 for all x, well, I can do the derivative of that and the second derivative of that, and that's still just going to be 0. So I'm going to plug this in, and it's going to be fine. Right, this is always 0, this is always 0, so 0 plus 0 is 0. Great. Let me maybe also check property 1 for D. So suppose I have, right, so in property 1, we were calling these V and W, but I'm talking about functions now, so let me call them F and G instead. But in any case, I'm supposed to be able to take two of my vectors in my vector space and verify that when I add them together, I get another vector in my vector space. So what does it mean for these to be members of my vector space? Well, it means, first of all, for F to be a member of my space, F double prime plus F is always 0. For G to be a member, G double prime plus G is always 0. I would like to conclude that F plus G is also a member. And, well, what does it mean to be a member? It means if I take whatever I want to check as a member of my vector space, if its second derivative plus itself is always 0, then that's how I tell it's a member. So here, let me write of x, f of x plus g of x. And okay, so we know how derivatives work. If I'm adding two functions and I take the derivative, I just get the sum of the derivatives. So the same is true of the second derivative. So if I take the second derivative of f plus g, I just get f double prime plus g double prime. And then what do I know? I know that this plus this is 0 from there. And I also know this plus this is 0 from there. So I've just got 0 equals 0. So the property checks out. Okay. So back to general vector spaces. Here's a couple of facts that just follow from the definition of a vector space. -1 is a scalar. If I take that scalar times v, I get this thing that we called negative v, which we also call the additive inverse of v. 0 is also a scalar. If I take that scalar times any vector v, I get the 0 vector. Also, if I take any scalar times the 0 vector, I get the 0 vector. So these are not things that I have to check for a vector space. These things automatically follow as long as it satisfies all the other properties. Okay, so let's define what a subspace is. So if V is a vector space over R, or it could also be the complex numbers, with whatever operations it has. A vector space is supposed to have addition and scalar multiplication. So assume that V is a vector space. If U is a subset of V, so U includes some of the elements of V, but not necessarily all of them. That's what this symbol means. So U is a subset of V. If it happens that U is also a vector space, using the same operations, that's when we say that U is a subspace of V. So, for example, in the examples that we just talked about, C was a subspace of A because, well, we didn't check all the properties, but I promise you that C really is a vector space. And it's also a subset of A. Like everything in here is a member of R to the n. Likewise, D is a subspace of B. Just because everything in D, they are functions from the real numbers to the real numbers. They also happen to have this additional property, but just by being functions from the reals to the reals, that makes them elements of B as well. And the next fact I was about to tell you is that if you already know that V is a vector space, you don't have to check all the properties for U to be a vector space. Some of them are what we call inherited, just by the fact that we're using the same two operations, addition and scalar multiplication, and that U is a subset of V. In fact, the only thing that we have to check, I can just check one thing, is that whenever I have two vectors in U and two scalars, that I can do this combination of them, so R1v1 plus R2v2, and that's a member of my subspace U. And that's, I'm going a little fast here, but that's basically because, like, I'm just putting up the first page again with all of these properties. A lot of them are inherited, meaning that they're automatically true just because everything in U is already in V and we're using the same operations. Like property 2 is inherited. If I'm adding two elements of U, then it doesn't matter what order I add them in because they are also elements of V, and I already know that it doesn't matter which two elements of V I add, or like what order I add them in, I mean. So a bunch of these properties are just automatically true in this situation. Okay, so what do I want to talk about next? Linear dependence and independence. So suppose we have a vector space, and I have some set of vectors, and there's finitely many of them. I'm going to just say that there's k of them, so v1 through vk. So I have these k vectors. I say that this set is linearly dependent if I can find k scalars, C1 through Ck, so these are in R, or if we were doing a vector space over the complex numbers, it would be in C. These scalars should not all be 0. Some of them can be 0, as long as they're not all 0. Such that if I take this combination, so C1, V1, C2, V2, all the way up to CK, VK, that's the 0 vector. Now, so let me point something out. This requirement is important. If I allowed all the C's to be 0, then it would be very easy to satisfy this equation just by letting all of them be 0. If all of these C's were 0, then this would automatically be the 0 vector no matter what. So we're not interested in that. What we're interested in is it possible for some of them to not be 0? That's a more interesting question. And, right. We say that the set of vectors is linearly dependent if it is possible to find these numbers C, not all 0, that satisfies this. So let's do something with that. So here's an example. I've got 3 vectors in R3, so these are 3-dimensional vectors. Each one has 3 coordinates. They're written as column vectors. And we're going to ask, are they linearly dependent or independent? And we're just going to use the definition. Well, so it's a question of, can I find C1, C2, C3? So if I take C1 times this, plus C2 times this, plus C3 times this, that equals the 0 vector. And the question is it necessarily true that C1, C2, C3 are all 0? Or is it possible that some of them aren't 0? So I'm trying to solve this equation, or more specifically, I'm trying to determine whether the only solution to this is when C1, C2, C3 are all 0. So actually, this turns into a linear system like what we're familiar with. If I just go across the top row, C1 times 1 plus C2 times 2 plus C3 times 4 equals 0. Go across the middle. Go across the bottom. Whoops. In other words, I mean, we really know what to do with this by now, right? Let me treat this. So C1, C2, C3 are like my variables. Let me treat this like a matrix. Okay, let me try to go fast and probably not end up going that fast. I got a 1 up here. I like that. Let me get zeros underneath it. So I'm going to do row 2 plus row 1, row 3 minus 2, row 1. Three, 0. This better be a 0. This is -1. This is -1, and then this is 0. Okay, I would like a 1 here. One idea is that I could swap these two rows. Of course, this is a -1, but then I could run a negative through here. Another idea is, I mean, this row is actually all divisible by 3. So normally I'm reluctant to introduce fractions, but actually I could divide this whole row by 3 and it wouldn't make any fractions. Okay, so I got my 1 there. I'd like a 0 underneath it. And I get zeros all the way. So remember how we interpret this. This is a leading entry. This is a leading entry in the second row. There is no leading entry in the third row. So I would say this, I label this column as leading. Also, this column is leading. This one is free. We learned how to express all solutions to this. Right now, we're not quite interested in all solutions. I can actually tell you the answer to the question at hand just by the fact that there's a free variable. The free variable could be anything. Like typically we set the free variable equal to s, and then we solve for the other variables in terms of s. But we don't really need to do that. The point is that there's infinitely many solutions. So there's definitely a choice for C1, C2, C3 that aren't all 0. In other words, these are linearly dependent. Okay. Let's attack B. I've got two functions. So these are members of my, these are members of my vector space consisting of all functions from R to R. And my first function is just the function that always gives me 1. It's like the constant function, f of x always equals 1. My second function is the function that gives me x, whatever I'm plugging in, f of x equals x. So I have these two functions, and the question is, are they linearly dependent or independent? So the question is, can I find C1 and C2, that are real numbers, so that C1 times my first vector plus C2 times my second vector equals the 0 vector. And when I write 0 here, of course, the 0 vector, when we're talking about this vector space of functions, this is the function that gives you, it's the identically 0 function, the function like g of x equals 0 for all x. In other words, well, f1 is my function that just always gives me 1. f2 is my function that always gives me x. And I'm going to set that equal to, I'll just write 0, but this is supposed to be true for all x. Oh, and yeah, before I go any farther, let me... So I didn't quite ask the right question. The question is, can we find C1 and C2 not both 0? Satisfying this. Of course, if they're allowed to both be 0, then you just let them both be 0 and you're good. Okay. The key is, this is supposed to be true for all x. So I can just plug in some convenient values of x. If I plug in x equals 0, this would tell me C1 equals 0. Now let me plug in something else for x. I'm not very creative. Let's plug in 1. If I plug in 1, this tells me C1 plus C2 equals 0. And I already know that the only way for this to work is for C1 to be 0. So C2 has to be 0. So, right. Now we can get confused about all of the negations, like the word not, but I would say the answer to this question is no. It is not possible to find C1 and C2 that are not both 0 satisfying this, because they do both have to be 0. The only way to satisfy this is if they are both 0. So we do not say that they're linearly dependent. We say that they're linear... I forget what I just said. We do not say that they're linearly dependent. We say that they are linearly independent. Okay. So let me give you a couple of shortcuts for telling whether things are linearly dependent or independent. So for our first example, we had a set of column vectors. We had 3 vectors in R3. So that's linearly dependent, and we actually saw this if and only if the system that you get by taking this matrix times x equals 0 has infinitely many solutions, where this matrix A we just make by putting the columns of V together. Actually, let me find that. Right, that's exactly what happened. Like we had these 3 vectors and we broke it down into this system. It's like this matrix is my A, and it's literally just this column, this column, this column, here, 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 and we set that equal to 0. So, and the question was, does that have infinitely many solutions? So that's all I'm saying in general here. Of course, we have a name for this, at least if k equals n, so we're talking about a square matrix. Remember that we said a square matrix A is singular if this system has infinitely many solutions, and non-singular otherwise. We also learned a connection between singular matrices and determinants. A matrix is singular when its determinant is 0. So we could do part A a different way, knowing this shortcut. I just make my matrix A. I'm just writing these columns down. And yeah, maybe I don't want to take the time to really do this determinant, but you can check that this determinant is 0. And then that's another way of showing that that these vectors are linearly dependent. Let me give you a shortcut for telling whether a set of functions is linearly dependent or independent. Yeah, I have to be careful about how I say this. So here goes. Say I have k functions from the reals to reals. We define this thing that we call the Wronskian, which is the following determinant. I put my functions across the top row, and then the second row is the derivative, so I just take the first derivative of each one. And then the next row would be the second derivatives, all the way down to the bottom row. And if I want this to be a square matrix, then when I get to the bottom row, I would be taking the k minus 1th derivative of each function. So I do that, and I do its determinant. And if this function, which is the determinant of this crazy matrix full of functions, if this function is not identically 0, meaning it's not 0 for all x, then our set of functions is linearly independent. And when I said I have to be careful the way I say this, it's because of this caveat at the bottom. If the Wronskian is identically 0, then we can't necessarily draw a conclusion. I'm leaving a little bit of information out because I don't want to go through what the definition of an analytic function is. It's possible sometimes to draw a conclusion, but I'm not going to tell you how and why. So for now, I'll just tell you the first part, that if the Wronskian is not identically 0, then your set of functions is linearly independent. So, yeah. Oops. In the interest of time, let me just go over example B again. So I'll write it this way. We had two functions. One of them was the function that always gives me 1, and the other function has the formula f of x equals x. So my Wronskian is, I put my original functions here. This is going to be a 2 by 2 matrix because there's two functions. Oops, there we go. And then I take derivatives, and I only need a 2 by 2 matrix, so I'm really only going to do one derivative. So 0 and then 1. And then this is actually a really easy determinant, right? 1 times 1. And the important part is that this is not identically 0. So identically 0 would be 0 for all x. In fact, this isn't 0 ever. It would be okay if we got something that is 0 for some values of x, as long as it's not 0 for all values of x. But as it happens, we got something that is just never ever 0. So that's fine. So these are linearly independent, and we already knew that the other way, but this is an easier way.